We'll go ahead and get started. Today we're really, I think today's going to be a short discussion unless y'all have lots of questions. What I want to do is show you an app on the phone, not on the phone, on the screen that kind of demonstrates how this sampling from a skewed population works. It's going to kind of demonstrate the value of the central limit theorem and really help us understand, I hope, how this sampling is really supposed to help us. Now, you have seen when you came in at the beginning of the year, you saw on my bulletin board that poster of How Old is a Penny, where last year's students, day after day for several weeks, would take samples out of my bucket of pennies and calculate the age. Well, we're going to simulate that today, and it works pretty well. It's not nearly as much fun as grabbing pennies out of a coffee can, but it's about the best we've got for now. But the idea here is, imagine a bucket of pennies, and this particular one has 1,000 pennies in it. And so imagine having 1,000 pennies, and you pull out a sample of a particular size N. We'll start with 10, sample size 10, and then we'll go to a larger one. And if you do that many times, every time you calculate the age of the penny, in other words, subtract the penny's age from this year, or the penny's date from this year, you get the age of the penny. So, and as you might imagine, that population is strongly skewed. The pennies in circulation there are more relatively new pennies than relatively old ones. Since I started doing this about 3 years ago with my students, anytime I get change back from wherever I am am addicted now to looking at the age of all my pennies. And so this may change the course of your life. You may look at it and say, this is the coolest thing ever. And you may look at it and say, it's just another one of Barry's dumb tricks. But anyway, we'll see how it works. So I'm gonna share the screen now, and we will jump to the screen. Can you all see a screen that has a bunch of graphs on it and stuff like that?
Yeah.
Yes. Okay, good. Okay, so let me introduce you to what you're going to be looking at. Up here in the upper left-hand corner is the literal population of our age of pennies. I can drag down through here, and I can see that all of these pennies have a particular age, and there are 1,000 of them in there. Now, you can also notice that this database was generated in 1999. So the second column here is the year of the penny, and you notice that its age is 0. So obviously, if we took this pile of 1,000 pennies today, we would get a different age, but we won't worry about that so much. If you look directly below here, here's a histogram of the actual database of pennies that we've got. So all of these pennies that show up as an age of 0, those are all minted in 1999. And as we go to the right, the pennies get older and the mint date goes down or gets farther back. So 99, 98, 97, all the way down. Here's some that are, I don't know, 40 years old. So that's a 1959 penny. And there's one in here that is from the 30s. So that's a wheat penny if you know anything about pennies. And if we ever get back to school, then in my bucket of pennies, I have a few wheat pennies that are really, really old. And so anyway, but that's the true population data. Remember, we rarely have this, but in this case, we do. And so in the middle part of the screen, this is how we're going to define how we're going to draw the samples. And after every sample, we'll see that data here. Each sample will show up here. And then over on the third graph, you'll see the accumulation of all of the samples that we take. So when I take a sample, let's just go ahead and take it. I'm going to take one sample, and it will be of size 10. So n equals 10. And first of all, before I draw the sample, let's make sure the 10% condition is met. I've got 10 pennies, or a sample size of 10. I've got a population of 1,000, so the 10% condition is met. And I'm good with the 10% condition as long as my sample size stays less than 100. If I wanted to take a sample size of 200 out of this population, then I can't guarantee that that 10% condition is met. I don't know anything about the shape of the population, etc. So we're going to keep our sample sizes relatively sensible, but I do want to make a point about a small sample size versus a large one. So let's go ahead and take a sample. So I drew one sample of 10 pennies. If you look down here in the middle screen, then you should be able to count 10 dots. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there are 10 dots here. Over on the left-hand graph, it actually shows you where in the distribution, which of the particular pennies were selected. And then on the far right graph, you see the mean age of those pennies. You notice down here, there's a blue triangle, and it shows you the mean of our particular sample. Up in the right-hand corner of the graph, you can see it. You can see the standard deviation, but it kind of marks the mean of the graph here, and the blue box represents that mean value. And you see here right now, the mean of this entire distribution on the right is 17.3. Okay. And because we only have one sample. So now if I take another sample, the first sample disappears, I get a new one, I have a new mean at 10 years old, and now I have a new dot here at 10 years old. So if I click on the dot, then I go back to the first sample. If I click on the next dot, then this is the second sample. You can see here that I have a total of 2 samples. And the other thing is this line here on the far right is the population mean, which if you go back over here, the population mean is 12.26. And so that line will never change. It stays the same. It's just kind of showing us where the population mean is. So let me take another sample of 10, and I'll do it again, and you can see the dots are piling up. Oddly, there we go. So as I keep taking samples, you can see down here in the middle dot plot, I can see they physically are changing. I can see the mean is physically changing, and I'm adding to my collection. So this graph on the right over here, if I took every possible sample of size 10 from this population of 1,000, ultimately I would end up with the sampling distribution of the sample means if I took every possible sample. But that's way too many. So I'll never get there. Eventually, I'll get to where I say, okay, that's enough. I'm going to use what I've got, and I'm going to approximate that. Okay, so far, I've had a total of 11 samples. To make things even, let me draw 9 samples all at once. And now you can see I've got a total of 20 samples here. And this is the shape of my distribution. So far, the mean for all 20 samples is 12.375. Standard deviation is 3.2 something. And you can kind of see the shape starting to form. Notice the population is clearly skewed right, but my sampling distribution, or my approximate sampling distribution, is beginning to show some symmetric shape. I wouldn't call it normally shaped yet, but it is single peaked. I don't think it's bell shaped yet. Let's add a few more samples. I've got 20 so far. So let's do 30. Let's get a samples, a total of 50 samples. Now, each of the samples, remember, is size 10. So now I've got a sample size, still got a sample size of 10, but I have a total of 50 samples. The mean of those 50 samples is 12.2, and it compares pretty well with the mean of the population, 12.26, okay? So that's what a distribution of sample size 10 looks like. And if I overlay the normal distribution over that, you can see it's skinny. It's tall in the middle. It's centered at 12.264. It's exactly what I would expect given what I know about my distribution, okay? So take a look, kind of freeze that picture in your mind. I'm going to change everything here. I'm going to reset. I'm going to reset now so that we don't have any samples. And now I'm going to change my sample size to, well, let's make it 30. Yeah, let's make it 30, and I'll draw one sample. Again, 30 samples is well less than 10% of 1,000, so I'm safe to go ahead and do that. So I draw my sample. Look at the shape of the distribution of that sample. It looks very similar to the population shape, which is what I would expect. Okay, but notice the mean of all those 30 samples. Man, it lines right up on top of the population mean. Let's draw another one. Again, my sampling distribution looks kind of like my population, but my sampling distribution of sample means, again, that's the mean of all of those 30 pennies, lines up really, really well. So I've got two samples now. Let's add 8 more. So now my total number of samples is 10, and I'm beginning to, again, I keep hovering around the population. Each of my individual samples, though, kind of reflects my population, but the mean of those is what I'm really, really, really after. Okay, so now I've got a total of 10. Let's do 10 more for a total of 20 samples. And the tent poles in the middle just keep getting bigger or taller and taller. Let's do 30 more samples. And look how narrow that distribution is. If I overlay the normal distribution, it's super skinny. Notice what happened to the standard deviation. It's really small compared to my population standard deviation. The mean is pretty close, 11 point, I think that would be 11.9 if I rounded it up, is pretty close to 12.2, okay? But the key thing here is that every time I take samples, the mean is really, really close to the population mean. My standard deviation is super small, so I get a very narrow normal curve, okay? So I'm going to do one more. I'm going to increase my sample size now to 50, which is pretty large. And I'll just take one sample here. Again, you can see where the data came from in the original population. My sample distribution looks very similar to the population distribution, but the mean of all of those data points, all 50 of those dots, the mean of those 50 dots comes out to 12.14. And let's do another sample. Okay, keep going. And you can just see, even though sometimes my sample distribution, my individual sample distribution, doesn't look much like my population. Here, this one's pretty uniform, where it doesn't reflect much skew at all, but it still came from the same population. So when I take a random sample, and the individual distribution can look like anything, but when I combine all of this data and start creating a sampling distribution of sample means, that's when things start to get really, really cool. So let's take a few more. I'll do them one at a time here, and you can kind of see how this middle graph changes with each sample. So that's a total of 10 now. Notice the standard deviation has gotten even smaller, 1.118 or about 1.12. The mean of my distribution here is right on top of my population mean, again, which is what I expected. So I've got a total of 10 samples. Let's add 10 more. Look at that sampling, that standard deviation. It's just dropping, dropping, dropping. And the mean of the sampling distribution, again, it's falling right on top here. So there's 20. Let's finish with a total of 50. So I'm going to do 50 or 30 more samples. And my standard deviation is hard for me to read, 1.36, I think. The mean of the sampling distribution is 12.25, maybe. I mean, it is almost exactly equal to my population distribution. So you can see what happens. The more samples I take, the better this estimate becomes. Notice that the shape of my population is definitely not normally distributed, but the shape of my sampling distribution of sampling means is normally distributed. There's a little bit of an oddball here and an oddball there, but in general, let me turn that off. The thing about it is the larger your sample size, the standard deviation gets so small that this is going to become a very, very, very skinny distribution to begin with. Now, one of the things I did is I fixed the x-axis scale down here to align with the population scale. I could change that. I could say I can rescale it so that it looks a little more natural based on the values that I took. And here, this becomes really, really, really easy to see that normal distribution. Now let me lay that normal distribution out. And you can see that looks, man, that looks so, so good. I have a few that stick up a little bit. I have a few spots that are a little bit low. But you can imagine taking these ones that are above the line, filling in these empty spots here, and those two areas would match up pretty well. Okay. So when we get done here, I will send you the link to this applet, and you can play around with it. There are a few other choices here. I think this one labeled Gettysburg, I think that's the exercise we did at the beginning of the year about the length of the words. I'm not sure what these other and Beyonce, I don't have any idea what Beyonce is. You might want to experiment and see what you get. But anyway, this is really where we are. We've got a population that looks like this. It's usually too large for me to really know what the population mean and standard deviation are. And so I take samples. The larger the sample size, the better off I am. And the more of those samples I take, the better picture I get of the population. Here I've taken 50 samples of sample size 50. Now, admittedly, it takes a while to count out 50 pennies. And it takes a while to calculate their ages and figure out what the average age is. But the cool thing is, if I do that, I get an idea of what the true mean of the pennies is. Now, one of the reasons I hope we get back to school is because I don't know what the mean of the population of pennies in my coffee can is. I don't have any idea. And so every year when we get finished with this, we look at it and we compare it with last year's data, and I have a pretty good idea of what the mean age is based on the sampling we've done, but there are 3,000 pennies in there. I'm not going to go through there and count this number. Maybe I'll have an energetic class one year that wants to take this on as a class project and give me the actual population. But right now, I don't know what the true population looks like. But I know that after we do several sets of samples, I can be pretty sure where the mean is when I'm all done. Okay. So that's really what I wanted to talk about today. Just give you an example how that sampling from an unusual distribution looks. And that gives us a chance to see how valuable, how important, how powerful the central limit theorem is for us here, okay? I'm going to stop here unless you've got questions. And there are two problems in the back of the textbook, problems 55 and 60 that I want you to take a look at for today. And again, I'll post that when we're done. I want to give you a little bit of a hint on problem 55. This is using a company that fills Coke bottles or soda bottles.
Do you know what page that is?
It's page 455. Okay, so this one's pretty straightforward. I think this one is what's the probability that an individual Coke bottle contains less than 295 milliliters? So that's just one Coke bottle. So this is more like the samples that we did yesterday, the example questions we did yesterday. So I want to reinforce what we did yesterday. And then look at number 60. I love this question because I'm a fan of storms. I really do love storms. And I love watching lightning. I have set out at times with my camera and tried to take pictures of lightning strikes. It's really, really cool. And so I'm always drawn to this question when we get here. But you can read the scenario. We think that there's the number of lightning strikes on a square kilometer of open ground in a year has a mean of 6 and a standard deviation of 2.4. There is a way for actually measuring that, believe it or not. It's kind of cool how it works. And there's this network, National Lightning Detection Network. And what they do is they sample 10 1 square kilometer plots of ground at a time. And so part A simply asks you to see what is the mean and standard deviation of that sample of 10. You should be able to calculate that. That's pretty straightforward. And then part B says, okay, wait a minute. Why can we not safely calculate the probability that the mean is less than 5 or the mean is any particular value? So you have to think, okay, what do I not have that I need to have in order to know what I need to know about part B? And then part C says, okay, we're going to take a sample of 50, sample size of 50, and then talk about how the central limit theorem applies in that scenario and what does it give me that I don't have in part B. So this will make you think about what does the central limit theorem actually help us do when we have a larger sample size, okay? So those two, and then that should help. And we'll get back together tomorrow. Any questions at this point? All right. No questions. Kind of a short class today. But I do want you to take some time. I think that applet will work on your phone. I hope it does. I haven't really tried it, but I'm told it does. If you don't have access to a laptop, but I do want you to go around and tinker with that applet some and do your own samples, pick your own sample sizes. I would encourage you to take a small sample size, 5, 10, 15, and then take a larger one, 25, 30, 50, and see what the differences are. Okay? And we'll go from there. All right, gang. Well, if you don't have any questions, I'll see you on the radio, as they say. Take care.